you all. Darrell Berry Jr. here, back for some more physics. I'll be reading chapter 5 of my graduate classical mechanics textbook while I compare it to the class notes as well. So we'll jump right into it. So chapter 5 is the rigid body equations of motion. Chapter 4 presents all the kinematic tools needed in the discussion of rigid body motion. In the other angles, we have a set of 3 coordinates, defined rather unsymmetrically, it is true, yet suitable for use as the generalized coordinates describing the orientation of the rigid body. And to remind ourselves what the Euler angles are, which we did so many videos ago. Here we go. So we have Euler angles of 3 successive rotations to the new coordinate. So we have Euler angle phi, the first rotation, about the z-axis. Euler angle theta, rotation about the new x-axis, and then Euler angle psi, which is rotation around the new z-axis. So these are the tools they're talking about. Maybe I'll copy these down. So if you recall, the generalized coordinates are the coordinates we use in the Lagrange equation to get the equations of motion. These are defining the Eulerian angles. In addition, the method of orthogonal transformations and the associated matrix algebra furnish a powerful and elegant technique for investigating the characteristics of rigid body motion. We have already had one application of the technique in deriving equation 4.86. I kind of hate how they scroll back and forth through all of the things. Here. We'll go to 4.86. So I remember how we derived 4.86, but maybe we should just copy it down. the basic kinematical law, the relation between the states of change of a vector as viewed in the space system and the body system. The space system is the coordinate system that's in free space that's fixed, and the body system is the axis that rotates with the body. These tools will now be applied to obtain the earlier dynamical equations of motion of a rigid body in their most convenient form. With the help of the equations of motion, some simple but highly important problems of rigid body motion can be discussed. Right? So 5.1, angular momentum and kinetic energy of motion about a point. I'll be referencing class notes as well to fill in any gaps. So I'll scroll through until I run into what I've seen there. Charles's theorem, Chasles' theorem states that any general displacement of a rigid body can be represented by a translation plus a rotation. Okay. Theorem suggests that it ought to be possible to split the problem of rigid body motion into two separate phases, one concerned solely with the translational motion of the body and the other with its rotational motion. Of course, as one point of the body is fixed, separation is obvious, for then there is only a rotational motion about a fixed point without any translation. But even for a general type of motion such as a separation, but even for a general type of motion, such a separation is often possible. The 6 coordinates needed to describe the motion have already been formed into two sets in accordance with subdivision. The 3 Cartesian coordinates of a fixed point fixed in the rigid body to describe the translational motion, and say the 3 Euler angles of motion about a point. Euler angles of motion about a point. If farther, the origin, so we have a body and move with and translate die. Those are our 6 coordinates. If farther, the origin of the body system is chosen to be the center of mass, okay, to 8 divides to relational center of mass and center of mass. Former term will involve only the Cartesian coordinates of the center of mass, the latter only the angle coordinates. So let's find 1.28. Hold up, 1.28. Oh my gosh, they're going way back into the how over that filled up in this one. Uh, yeah, this doesn't go back that far. Damn. Equation 1.28. This is the angular momentum. Position across the mass times velocity. Position, position across momentum. This is total angular momentum about, oh, I do vaguely remember this derivation type deal. Former term will only involve the Cartesian. A 1.31, a similar division holds for the total kinetic energy, which can be written in the form, crap. They go back to 1.31. Kinetic energy equals 1/2 m v squared plus 1/2 sum I m I v prime. Back then we were dealing with the prime coordinates. equals 1 half mv squared plus t prime by theta psi. All is 1.3. And as the sum of the kinetic energy of the entire body as if concentrated at the center of mass, plus the kinetic energy of motion about the center of mass. So the kinetic energy of the movement of the center of mass and the kinetic energy of things spinning around the center of mass. Often the potential energy can be similarly divided, each term involving only one of the coordinate sets. Let me check the notes here. So we should go into angular momentum next. Often the potential energy can be similarly divided, each term involving only one of the coordinate sets, either the translational or the rotational. Thus, the potential energy in a uniform gravitational field will depend only upon the Cartesian vertical coordinate of the center of gravity. See what the star says? The center of gravity, of course, coincides with the center of mass in a uniform gravitational field. Seems like there's problems in a non-uniform G. Cartesian coordinate of the center of mass, a uniform gravity in vertical. Or if the force on a body is due to a uniform magnetic field B acting on its magnetic dipole moment M, and the potential is proportional to MB, which involves only the orientation of the body. Certainly, almost all problems soluble in practice would allow for such a separation. In such a case, the entire mechanical problem does indeed split into two. The Lagrangian L equals T minus V divides into two parts, one involving only the translational coordinates, the other only the angle coordinates. The two groups of coordinates will then be completely separated, and the translational and rotational problems can be solved independently of each other. Yes. It is of obvious importance, therefore, to obtain expressions for the angular momentum and kinetic energy of the motion about some point fixed in the body. So solving these problems, you need to get the angular momentum and kinetic energy about a fixed point in the body, ideally the center of mass. To do so, we will make abundant use of equation 4.86, which I believe I copied. All right. Making derivatives relative to a coordinate system fixed at some point in the rigid body. It is intuitively obvious that the rotation angle of a rigid body displacement has also the instantaneous angular velocity vector is independent of the choice of origin of the body system of axes. The essence of the rigid body constraint is that all particles of the body move and rotate together. However, a formal proof is easily constructed. Let R1 and R2 be the position vectors relative to a fixed set of coordinates of the origins of the two sets of body coordinates. Right? So saying that we have a single body, but we're treating two parts of that body as separate things. Uh, 2, 2, V prime 2, V prime 1. Make these stand out a little bit. Purely relation between sets of rigid body coordinates with different origins. Right? That seems accurate enough. If the origin of the second set of axes is considered, right, maybe I should draw these lines better. Origin of the second set. The origin of the second set of axes is considered as a point defined relative to the first. Then a time derivative of R2. Oh, I forgot to put my time derivative of R2 relative to the space axes is given by are they using the space thing? I think so. Oh, hold up. I'm not seeing how they're getting that. R dt space space minus there's 2 dr over dt1 plus dr over dt space minus dr1 1 over dt space plus omega 1. Not sure how they got this. The last step follows from equation 4.86. Yeah, I don't see how they're applying that though. No less. B dt space equals d dt one plus r I plus omega r r1 plus. How does that become omega 1? Taking the derivative of r2, less I keep the r2 on the left side. This becomes d r2 over dt space minus d r1 over dt body. How do you get that? I have to ask. Calling that the derivatives of r relative to any rigid body axis must vanish, and with W1 as being the angular velocity vector appropriate to the first coordinate system. Alternatively, the origin of the first coordinate system can be considered as fixed in the second system, with the position vector negative r. In the same manner, then, the derivative of the position vector r1 to this origin relative to the fixed space axis can be written as that. It could also be 1, 2, 2, 2. I see one thing that happened. The document has a typo. Looks like that's an equal sign. That will definitely make confusion. Check this out really fast. ER2. Oh, I don't know why it's confusing. Because the document left off all kind of equal signs. All right, everybody just read this one. And read this one in the paper book. These errors in the book are throwing me off. Try to do a better job of just writing it out. You correct the equations here with the it says that the origin of the second set of axes is considered as a point defined relative to the first, when the time derivative of R2 relative to the space axis is given by, so again, we're supposed to be using this equation here, 4.86. So let me just erase this and I'll start this over without the typos from the book. We're going to apply this equation to get the derivative of R2. So we have d dt R2 base equals d dt R1 plus R, as was defined initially, base, which equals d dt base plus d dt R base. Okay, so that's working out so far. And then we have the right side, which is we got should this over here. This, and then we have the right side, which equals d dt R2 R for body plus omega cross R2 equals d dt R plus d dt R omega cross. So that equals So they're saying derivatives of R relative to any rigid body axes must vanish. This equals, I'm gonna write this all out, d dt 1 d dt r r plus w cross r1 plus w cross r. R relative to any rigid body axes must vanish. Okay. Because of the rigid body, the particles don't change amongst themselves. So, so this will be zero. And with W1 as being the angular velocity appropriate to the first coordinate system. W1. Alternatively, the origin of the first coordinate system can be considered as fixed to the second with the position vector negative r. In the same manner, then the derivative of the position vector r1 to this origin relative to the fixed space axis can be written as, but first let's work out the last part of this one. It gets space on that part. Omega 1 R1. So this should be zero since they're going in the same direction. I'm not sure where the R1 goes there. So we have d R2 over dt space equal d R1 over dt. This is also space, which I'm not sure about. Plus, they say that will vanish. This was still the left side. I was thinking I was switching to the right side already. S plus the R dt S. So if I also color code this, we have this first part is this. We have Second part is here. And then we have equals d dt. We do have a space where I thought it would be body. Plus omega 1 cross. About this one. Now we can write the other part. Mm, So we have to swap all the numbers. Make this 1, make this 2, make this minus, make this minus, make this 2, and make this 2. A comparison of these two expressions shows that omega 1 minus omega 2 cross r equals 0. Any difference in the angular velocity vectors at two arbitrary points must lie along the line joining the 2 points. Assuming the omega vector field is continuous, the only possible solution for all pairs of points is that the two angular velocity vectors must be equal. Also, the angular velocity vector is the same for all coordinate systems fixed in the rigid body. The rigid body moves with one point stationary. The total angular momentum about that point is equals total angular momentum about we went through several equations already. It's the first numbered one, implying this amazing invention where Ri and Vi are the radius vectors and velocity, respectively, of the ith particle relative to the given point. Because Ri is a fixed vector relative to the body, the velocity vector Vi with respect to the space set axes arises solely from the rotational motion of the rigid body. The center of mass is not moving, so it stays still. Only rotational kinetic energy. Equation 4.86. The r dt So we have uh, dr over dt. I will say dri over dt equals dri over dt space body plus omega cross ri. So this is vi equals, and it's fixed, doesn't change. So we have to make use of 4.86 to convert between the body and space systems. Hence, equation 5.1 can be written as L equals M I R I times V I, which equals M I R I cross omega cross R I equals, oh, that's it. Expanding the triple cross product. And I had that recently. I looked at the triple cross product. Oh, it was the other day. Should be up in here. Saw it before me. Let me know. I'll just scroll down. If I don't see it, I think I remember it. Uh, A cross B cross C equals, I don't remember what it is. Let me look it up. It's like I was remembering it. So this equals MI R I dot R I omega minus R I dot seems right. So L equals MI R squared omega minus dot omega. We have that. And this is a magnitude just by the definition of the dot product. We did that a while back. And let me check the notes. Almost to the next part. L equals MI RI squared minus RI R3. And this is 5.3. Again, expanding the x component of the angular momentum becomes expanding the x component. It says again expanding. All right, so I'm starting to remember this is something professor did. Quite yet. How do we expand this? And we have L. This is from class equals I omega. MR squared is I. I need to learn how to expand this. Equals M R squared omega M I. I had to have recorded this derivation somewhere. So we have omega x, omega I, and omega z. Let's expand that first. I R squared z is M I R I dot. Oh, doing this incorrectly. Omega x, omega to be more particular. M squared omega x I plus omega j plus omega z k M I. So do x j K dot copy this down. So this equals MIR squared omega X plus M squared omega J plus MIR squared Z K minus MIR plus minus MIR J minus MIR K. Yeah, that's right. The dot product is the dot product so the dot product is WX, WY, WZ. Right? Looks like it's getting a little closer to what they have. Equals M squared WX minus WX MI squared minus R X M Y squared minus R X I J plus M omega D M I This is swap I squared minus R. This is ever closer to what they have. This is V. Right. So what we're going to do is just take the one we have W M squared minus X I V equals W X M I squared minus X I squared. I minus X I Y I J minus X I Z I K. So that means that L equals omega squared X I squared minus RT. All of these are added together. You have to separate them again. Two. X M I R squared X I minus X I. Then you have the vector. You have that. We have W Y squared minus I times the whole vector. So that's W Y M I R I squared minus I squared I minus J, I, Z, I, K. All right. You have the same. And I put them up according to the I, J, and K's. I should have did this differently. Let me scroll back a bit. The word. Seeing if I missed anything. So that this has a vector on it, but the second part doesn't because of the dot product until the aura is expanded. So that's where I messed up at. You notice in I notice in the book there's a I term that stays separate. It goes to both of them. I need to erase from here. All the terms have the dot product part. I'll just keep them together. Equals m r squared wx I minus m I squared wx minus mi. I'm going to expand this completely. Mi x j plus vi k Wx plus mi squared wyj minus mxii plus yij plus zik uh, squared wgk minus mj plus zik I here. This equals most of this will stay the same. I think I can make do with a bunch of copy paste. These will get an mi. So, and I believe the second line is exactly the same, except there's a y, a wy at the end. And the next line is exactly the same. There's a wz at the end. Right. See if I can work with some copy paste again. This is going to equal this I minus this I minus this I minus this I plus this j minus this this j. Distribute my negative. J minus j minus j plus mk minus mk minus mk. I have to include those in somehow. do that by simply putting the parentheses back. Now I do have to put a plus. You want to keep the parentheses where it's at. There's a minus on the outside. We'll go back. I'm on my way there. I have m squared wx minus 3 mi xi for the dropped off more terms. I dropped off my to the 3 should be because there's different terms. All right. I'm not seeing how to expand this thing, but I think we get the idea that we expand and do all this stuff here. We end up with, let's call it expand. So x equals wx mi r squared minus xi squared minus omega y mi xi yi minus omega z mi xi z. 5.4. Let's similar equations for the other components. See if I can derive what the others will be, or divine what the others will be. Z equal L equal I equal be like this. This will be M- this will be WY minus Y squared YZ. This last one, the YZ. The Y, the Y, and this one should be the ZI squared. YXZ, YX, YZ, ZI, ZX, ZY, and ZZ. So it should look something like this. The similar equation for up to. Thus, each component of the angular momentum is a linear function of all the components of the angular velocity. So this is the angular velocity. You can see it there. So each component of angular momentum is a linear function of all components of the angular velocity. Angular momentum vector is related to the angular velocity by a linear transformation. To emphasize the similarity of 5.4 with the equations of linear transformation, 4.12, we may write Lx as, I should have 4.12 up in here. Here's 4.12. We have Lx equals Ixx omega x plus y omega y plus z omega z. Ly equals Iyx omega x plus Iyy omega y plus Iyz omega z. And Lz equals Izx omega x plus Izy omega y plus Izz omega z. 5.5. Coefficients Ixx and so forth. So I, Ij are coefficients. Element of matrix transformation. The diagonal elements are known as moment of inertia coefficients. Ij when I equals j. These are moment inertia coefficients. J I equals not J has the form J equals negative M I J. M J. J, if they're equal or the same, if they're not equal, then I to write it how they wrote it, so I don't diagonal moment of inertial coefficients. Diagonal. So we have I y equals M I y 5.7. In equations 5.6 is 5.7. The matrix elements appear in the form suitable, but the rigid body is composed of discrete particles. For continuous bodies, right? I think this is a good place to stop. I've been going for about 2 hours. So I'll take a break. I'll probably come back, if not later or another day. Probably will get some sleep soon. If you like, subscribe if you haven't already. Make some comments, and I'll see you next time.